Okay, Leonardo, this is the lesson about limits, continuity, and partial derivatives. The topics that we are going to see is limit of function of two variables. Now, for two variables, we need to define a disk in the plane. The definition of limits is related with disk in the plane. So you approach to a point, and the point is x0, y0, on a surrounded of the point that is a disk. We will see the formal definition of limits. We will see what it means for a function of two variables to be continuous, and we'll see the concept of partial derivative. So let's go to start. First things, we are going to define an open disk. What is an open disk? You center the disk at the point x0, y0, and you imagine that surrounding the disk, surrounding the point is a disk of radius delta that inside the disk there are many points x, y. And all these points, the distance from the center to the point inside the disk, they are less than the radius. So is the interior of the disk. It's strictly the interior of the disk. That is why we are talking about an open disk. So this is the point x0, y0. You create a disk of radius delta in the plane xy, and inside the disk there are xy points, and the distance from any point xy to the point x0, y0 is square root of x minus x0 squared plus y minus y0 squared. We are paying attention to points that are inside the disk. So this is less than the radius delta. So what is a complicated definition for a function. The limit definition is quite strange and complicated, but this is the definition. What we mean by the limit when the point xy tends to x0, y0. When the point xy is approaching the point x0, y0, what happens with the function fx, y? If we say that when you are approaching to the point x0, y0, f is approaching to L, to the point, to a number L, what it will mean this? It will mean the following thing. Imagine this is the theta axis. This is the theta axis. This is where the function f of xy takes value. So if I choose a point here, xy, let's say here inside the disk, the point will have an image f of xy on the theta axis. Let's say that for this point xy, the image is here. So this is f of xy. Let's say that I'm approaching to the point x0, y0. You see, I'm approaching. I can approach the point x0, y0 from different paths. I can approach from here to the point, or maybe I can approach from here to the point x0, y0. I can approach in different ways. And for every way that I approach, the image of the points will be somewhere here. So what are the definition of the limits? When you are approaching the point x0, y0, the center of the disk, wow, what will happen? What is the condition that the limit L exists? Let's say that the limit L exists and is here. So now you fix epsilon, a distance from the point fxy from here. This is the point xy, or this is the point xy. This is f of xy. You mark a radius around the L of radius epsilon. So the distance of x of xy, the distance from x of y to the distance L, is less than epsilon. Is inside the interval. So for every epsilon that you choose, it's always possible to choose a disk of radius delta that all the points are inside. And the formal definition is exactly like this. For that you choose, for every epsilon that you choose, epsilon of course is greater than 0, exists a delta bigger than 0, of course, a delta here on the circle, that if the distance between the value of the function of the point xy, this is the point xy and this is the value of the function, if the distance between L and fy, the distance between f and xy, if you suppose that here is the 0, this is f of xy, and this is L. So the distance is the absolute value of L minus f of xy. If the distance of f of xy minus f is less than epsilon, so it is possible to find a disk of radius delta such that all the points are containing in the disk. So the distance between the point x and x0 and the distance between the point x0, y0, the center, and the point xy is less than delta. It's a complicated definition that is not very useful. It's not very useful, but the idea is that because this is valid for all epsilon, when you stretch the epsilon, you need to find a delta here, a radius delta, where all the points goes inside the interval between L plus epsilon and L minus epsilon. L plus epsilon, L minus epsilon. If you change the epsilon, you change the delta. So there is delta of epsilon, such that for every epsilon that you choose, there is a delta where all the point goes inside the epsilon interval from L minus epsilon to L plus epsilon. So this is the idea of limits. Let's go to review. A function of two variables is continuous at the point x0, y0 if the limit exists. There are three conditions here. First thing is 1, the limit when x, y approach to the point x0, y0, and it approach by any path of f of xy exists. A function is continuous if there are three conditions. The first condition is that the limit exists. The second condition is that f of x0, y0 exists. And the third condition is that the limit when x, y tends to x0, y0, when you approach to the point x0, y0, the limit of the function is exactly the value of the function at the point x0, y0. This continuity these limits allow us to define partial derivatives. What is the partial derivative respect to the x? The partial derivative of the function respect to the x of f sub x comma xy is the limit when delta x tends to 0 of f of x plus delta x comma y minus f of x comma y divided by delta x. What it means, the partial derivative? It means, see this picture, there is a function here, there is a function here, there is a function. So you see the partial derivative of the function respect to the x at certain y0, at certain y, you move in the plane, in this plane, parallel to the x-axis, and you find the derivative when y0 is fixed. If this is the imagine that this is the function, let's say, and you see the value of the function, at the point x. You see the value of the function at the point x plus delta x. Okay, you subtract f of x plus delta x minus f of x. But now the function is of two variables, so what you are subtracting is f of x plus delta x comma y0 minus f of x comma y0 divided by delta x. This is the slope at y0 when y0 is maintained constant. So this limit, the limit when delta x tends to 0, is what we call the partial, with a curly d, the partial derivative of f respect to x when y is constant. This is the idea. Let's go to x. So the summary of this lesson, that is that, well, we continue to study functions of two variables or three variables, and we extend what we know of one variable to two or three variables. Okay. Now, example 1. What is this limit? When the function is defined at any point x and y, and what will be the limit when x comma y approach to 1 comma 2? Well, when x approach to 1, this x become 1, and when y approach 2, this y become 2, this x become 1 square, and this y become 2 square, so the limit will be 2. Is this a continuous function? Is continuous? Well, it's defined at all x comma y. The limit at the point 1 to the limit exists, and the value of the function is also 2. So if the limit exists and the value of the function is 2, this function is continuous. Okay, it will not example 1, so let me write again the condition for continuity of a function of two variables. The first condition is that the function at the point x0, y0, the value of the function exists. It's a number. Okay. The second condition is that when you approach to the point, the limit exists. And you approach to the point by any path, and the limit exists means that by any path that you choose, the limit will be the same. And the third condition is that 1 and 2 agree. If 1 and 2 agree, we say that the function is continuous. So if the value of the function and the limit of the function when x comma y approach to x0, y0 have the same value, we say that the function is continuous. Example 2, when the limit cannot exist. Let's say that we have the function x squared minus y squared divided by x squared plus y squared. So we have to uh, prove that the limit does not exist. To prove that the limit does not exist, we take two paths to approach to the point 0, 0. For example, we can approach to the point 0, 0 by a rectilinear line, or we can approach to the point 0, 0 by a parabola. If the limit is different, so the limit will not exist. So the first path is the rectilinear line with a slope 0, that is y equals 0. When y equals 0, the limits of x comma 0 approaching to the point 0 comma 0, it will be x squared minus 0 squared divided by x squared plus 0 squared squared, and this limit is 1. Now, if you approach through a rectilinear line y equal x, the limit will be of the point x comma y, but y is x, s comma x, approaching 0 comma 0. What will be the limit? It will be x squared minus x squared, which is 0, and in the denominator will be x squared plus x squared 2x squared. 0 divided by 2x squared is 0. So approaching through the rectilinear line y equal x, the limit is 0. Approaching to the rectilinear line y equals 0, the limit is 1. Then the limit doesn't exist. And remember that y equals 0 is the x-axis. You are approaching to 0, 0 through the x-axis. Y equal x is the rectilinear line that is on the plane. Here is y equal x. You are approaching to the point through the rectilinear line y equal x. Okay. When it will not, well, this part you know how to do it, is calculate the partial derivative of the function f of x comma y x cubed plus sine of y. The partial respect to the x, you maintain the y fixed, so you consider sine of y like a constant. So the partial of f respect to the x maintaining y constant, so sine of y is a constant, is 3x squared. And the partial of f respect to the y maintaining x constant is cosine of y. So these are the two partial derivatives. Example 2. Now you can read here the study tips. If you can read the pitfall, let's go to read the pitfall. It's saying example 2, you cannot plug in 0, 0. Why? Because example 2, in the denominator is x squared plus y squared. If you plug in 0, 0, you have in the denominator 0, 0 squared plus 0 squared. And you cannot divide by 0. So it doesn't exist, the function, the value of the function. The function is not defined at 0, 0. There are a lot of notation for partial derivative. Okay. This is one notation, f of x. The partial derivative of f respect to the x, or the partial respect to the x of f of xy, or the partial of c respect to the x of theta x. Many different notations for the same concept of partial derivative. Here there are some problems to do. Maybe you can choose one of the problems and to solve it. Well, I hope it is helpful. Let me know if you need something else.